sugars, amino acids, fats. And today we'll hammer home a little bit by thinking about growth and metabolism, the regulation of metabolism by thyroid hormone, and also we'll finish up with thoughts about calcium regulation, because after all, we need calcium to make strong bones, right? And bones are associated with growth, right? And growth is associated with growth hormone, right? And with growth hormone induced insulin-like factors from the liver. So you've already studied it. You've already viewed the lecture. Let's do review by answering questions on digital dialogue under April 6th. Question 1. Seems to be slow to respond for me. Maybe you're already done answering it. Go ahead and be answering it while mine's coming up.
Mine's not loading either. Learning Suite might be having problems.
Yeah, me neither. I can't get it.
Okay, thank you. Maybe everybody's starting off at once this morning.
Mine says Learning Suite itself is having difficulties.
Well, what if the difficulties are substantial? While we're waiting for Learning Suite to recover from the onslaught of people trying to use it this morning, let me pose the questions as best I can remember them, and you be thinking your answers. What region of the adrenal gland releases epinephrine? What region releases sex hormones? Cortisol, aldosterone. Answers are, you gotta make sure and remember that this capsule down here is near the kidney, so that you can realize that the medulla in the middle is at the top of this histological section. And remember that the preganglionic nerve coming from the lateral horn and passing right through the sympathetic chain goes all the way to the adrenal medulla and stimulates it to release epinephrine, which is a catecholamine. Sex hormones, what are we talking about? The zona reticularis, just superficial to the medulla is the way we would say it in anatomy, is responsible for secreting testosterone and estrogen in men and women. And the testosterone is actually important in women because it stimulates the sex drive in women. By glucocorticoids, we're referring to cortisol, which is a sugar-inducing agent. So cortisol from the zona fasciculata, and then aldosterone, this is a reminder that that comes from the adrenal gland under the stimulus of angiotensin II, which is released or cleaved from angiotensin I by ACE, and angiotensin I being cleaved from angiotensinogen by renin, released from the kidneys, from the juxtaglomerular apparatus and the nephrons of the kidneys. So glomerula, glomerulosa, juxtaglomerular apparatus. That's a mnemonic. Another mnemonic might be in this diagram. The zona glomerulosa is close to the glomeruli of the kidneys. but it wouldn't be if you were looking at this section up here, then it wouldn't be as good a mnemonic. But either one of those might help you remember that this name, glomerulosa, is where aldosterone is released. Next question, still no news from Learning Suite, is cortisol anabolic or catabolic? And while we're at it, let's get it straight, since I goofed up last time, for which I'm deeply sorry, and Morgan graciously corrected me. What about insulin and glucagon? Anabolic or catabolic? Be thinking your answers, maybe jot them down on a piece of paper. Let me see if I can get it straight before I flip to the slide. Insulin. Oh, yeah. I got it right this time. And what about cortisol? Oh, yeah. I'm ready. Everybody ready? So to avoid, oh, by the way, those who have arrived lately, we're having a hard time seeing digital dialogue, so we're just winging it here without it. Cortisol is catabolic, meaning it stimulates protein breakdown in the liver so that pyruvate can be made from amino acids and sent through the bloodstream for production of glucose. Sent through the bloodstream, I want to say that's right.
So is that gluconeogenesis?
Yes. Can you see my pointer? Or are you not looking at the slides, which I have shared?
I can't see your pointer.
I've always assumed that you guys could see my pointer, that was the
Oh, there it is.
merit.
Yeah, we can see it.
Now you can see it?
Mm-hmm.
Gluconeogenesis, exactly. It helps cause protein breakdown in muscle. Oh, I know, I said it backwards. The protein breakdown in muscle sends the pyruvate to the liver to build, where the liver can take it and build up glucose. And then fat tissue breakdown. So it's basically catabolic, break things down, catabolism, break things down. Whereas insulin, that stimulates glycogenesis, building up glycogen in liver and muscle. So it's anabolic. And glucagon breaks down glycogen so that it can be released into the bloodstream, and that's therefore catabolic, like cortisol. But then if cortisol, I always get asked this question, if cortisol is so darn catabolic, why is it in Cushing's syndrome that you get obesity? If it's breaking down lipid and protein, why would you get a humped back and puffy cheeks? Well, the answer is, and this isn't probably something that Morgan pointed out, tell me if it is, Morgan, it stimulates redistribution of fat, more high trunk fat, more behind the shoulder, brown fat. In bears, it's important for preparing for hibernation. So when fall is here and the cold is coming on, the long-term stress results in more ACTH release from the anterior pituitary gland and buildup of their thermogenic fat stores, the fat that's going to be used to keep them warm while they hibernate all through the winter. So yeah, it's true that it is catabolic and breaks down white fat stores, but it builds up brown fat stores. And furthermore, think of a bear now, getting ready for the winter. What do they have to do? They have to overeat. They have to eat for the whole winter. What stimulates them to eat more? Oh, the hypothalamic the appetite center. The appetite center. Well, the cortisol also stimulates the appetite center. So although it's catabolic from a metabolic point of view, it still stimulates you to eat more. And the contrast, or I should say, how do I want to put it? Antithesis, similarly counterintuitive point is that if the cortisol is low, you'd think, aha, I'm going to get fat now because I'm no longer catabolic. But to the contrary, when you have low cortisol, you have Addison's disease, and Addison's disease is associated with fat and muscle wasting. Not so much because you're all of a sudden catabolic instead of anabolic. No, you're less catabolic now, but because your appetite center is less excited, less activated. And so even though it's catabolic, it makes you fat. And when you don't have it, you get skinny. Weird, eh? Good counterpoint or counterintuitive point to remember when you get into the clinic. Still no luck loading the discussions in digital dialogue. I guess Learning Suite is just dead in the water, so let's move on to remind yourself what we learned about primary and secondary hypercortisolemia for just a second. Remember that there was feedback that stimulated, that inhibited ACTH release when cortisol is high. So if you have primary hypercortisolemia, you'll have low ACTH and low corticotropin releasing hormone, where corticotropin is a synonym for adrenocorticotropic hormone. Reminder of that. Reminder too, that Morgan undoubtedly mentioned, that cortisol not only is catabolic, but it's also inhibitory for the immune system. It knocks down immune reactions. So when people are having trouble with excessive immunity, using cortisol-like hormones is a good way to knock that down. But you need to do it temporarily, because that will result in hypercortisolemia, which takes time to recover from the inhibition of the hypothalamus and the anterior pituitary gland. Notice that the cortisol level rises in the morning. Where is it? Rises in the morning about waking time. Might be what wakes us up in the morning, and then it has a circadian pattern that in the late afternoon it's high, at midnight it has a little bump, but it's highest just in the morning when we wake up. I don't have a real good mnemonic or physiological why that is. Might be related to the stress of the day or something. But the point is that this circadian rhythm is processed through neurons that affect the hypothalamic neurons that release corticotropin releasing hormone. I was able to get Learning Suite to respond, but not bring up digital dialogue yet. Keep waiting. It's interesting just to remind you that cortisol is part of this matrix of cholesterol-based molecules. And we're going to come back cholesterol at the end. I'm excited about this because I hadn't realized this until last night when we talk about vitamin D. So keep this in mind. But right now we're talking about the adrenal gland. This matrix takes place in the adrenal gland. There's a series of enzymes that catalyze these molecular changes, oftentimes hydroxylations or sometimes ring changes. So that from cholesterol we can make progesterone, which through 21-hydroxylase gets converted eventually to corticosterone. Corticosterone is a glucocorticoid like cortisol, and there are others too, that can come out of the zona fasciculata of the adrenal gland. Corticosterone is converted. There's more enzymes in the zona glomerulosa of the adrenal gland that are used to convert corticosterone into aldosterone. Or if a different chemical modification pathway takes place, we can get female hormones, estrone and estradiol. And we can get male hormones, DHEA, androstenedione, testosterone, and the potent final product, dihydrotestosterone, out of the adrenal gland, whereas we usually think of these coming from the gonads. They also come in small amounts from the adrenal gland, small and steady, and not as responsive to sexual stimulation as the gonad release in the males, or pregnancy preparation in the females. How about thyroid hormones? Anabolic or catabolic? What do you think? It doesn't really say, does it, anywhere? The circles, Morgan might not have known to point out, are what I focus on in these slides, because these tables are fairly big and overwhelming. So I try to focus you in on something to get you started. Thyroid hormone stimulates metabolism. We've been talking about metabolism. We've been talking about glycolysis, ATP production. And if you're stimulating glycolysis and the citric acid cycle, you will use more oxygen. So thyroid hormones stimulate oxygen consumption throughout the body. In particular, the physician notices that it stimulates the heart rate. You get an increased heart rate and pulse strength when you're hyperthyroid. It also raises your core body temperature a bit. It's catabolic, breaks down proteins in adults. Now, interestingly, it's anabolic in children, building things up. And part of the way to remember that is children grow stronger because of thyroid hormone, and especially their brain. Baby's brain depends on exposure to thyroid hormone. Without it, you don't get normal development of the nervous system. And one of the most disturbing problems with thyroid hormone is cretinism, the lack of exposure, I believe it's in the womb, to thyroid hormone, resulting in severe mental retardation. We called it in the old days, cretinism, the lack of brain development. I'll expect you to know about how thyroid is produced in the colloid as a thyroid hormone. Starts out as a glycoprotein that involves tyrosines getting clipped. And T3 has what? It's two back-to-back, piggyback tyrosine side chains, one piggybacked on another, with iodine attached. And the iodine has to be transported in to these follicles through the epithelia that surrounds the follicle that contains colloid in the center. And I'll expect you to be clearly aware that there's transport of iodine through the basolateral and apical membranes using sodium iodide co-transport in the basolateral membrane and facilitated transport of iodide in the apical membrane. The ID terminal termination on an atom's name implies implies that it's an anion. So iodide as an anion is taken up, are gained together, exported through endocytosis, clipped off of the glycoprotein backbone, and then secreted into the bloodstream. So the next digital dialogue question was going to be this. We're contemplating what is myxedema, goiter, and Graves' disease, and what do you do to fix a goiter? I'm quite sure I had some question too about how to, whether they were anabolic or catabolic problems. You'll recall that from anatomy, if you took it, that goiter is due to iodine deficiency. Why though? Why would iodine deficiency result in a buildup of tissue when thyroid hormone is catabolic in adults? Shouldn't it break down tissue? Now, I like to emphasize at this point that there's a difference between the word trophic and tropic. And our textbook author doesn't make that distinction the way it's traditionally been made in medicine and still is, according to what I can find on the internet. Trophic means to cause the growth of tissue, whereas tropic means to stimulate hormone release in a tissue. Adrenocorticotropic hormone stimulates cortisol release from the adrenal gland. Thyroid stimulating hormone is a trophic hormone that will stimulate the thyroid gland to grow if it's present in excess. It would be present in excess if you're lacking the feedback. So without negative feedback, when you have low iodine, you can't make the T3, T4 because there's none in your blood, not enough, to get transported in as iodide into the thyroid gland to make thyroid hormone. So having none in your blood, you don't get this negative feedback loop. So you make excessive thyroid stimulating hormone. In fact, excessive thyrotropin releasing hormone, which is tropic on the thyroid gland, stimulating the thyroid gland to release thyroid stimulating hormone. Sorry, I meant to say the anterior pituitary gland to release thyroid stimulating hormone, which then goes to the thyroid gland and stimulates its growth. It's trophic as well as tropic. So it stimulates the growth, and that's what a goiter is. A grown, enlarged thyroid gland due to the trophic effect of the thyroid hormone. It is thyroid stimulating hormone. Trophic makes the gland grow, as well as tropic, making the gland secrete its hormones. What is Graves' disease? Here's the funniest thing. I once had a friend named Lord Monckton. He came to visit me from England, and his eyes bugged out like this because, as he told me, he had hyperthyroidism, Graves' disease. It's the weirdest thing. Counterintuitive, no explanation from the point of view of catabolic. Fat pads behind the eyes increase in size when you have hyperthyroidism. I guess it's kind of like cortisol that way. You know, cortisol builds up brown fat and reduces white fat. Thyroid hormone builds up the fat pads behind the eyes, even though it's generally catabolic for protein. muscle protein throughout the body. So even though your fat pads are building up behind your eyes, your muscles are getting thin throughout your body when you're hyperthyroid. Why would you be hyperthyroid? Because of antibodies. It's an autoimmune disease that stimulates the production of thyroxine, which is tetraiodothyronine, or triiodothyronine with 3 iodides. Triiodothyronine, T3, is a little bit more effective than thyroxine in the bloodstream, but they both bind to the same thyroid hormone receptors and have the effect of increasing metabolism. So a person with Graves' disease, their eyes would be bugging out because of the specific
What do we do if video stops?
This is a disaster today.
Yeah.
it's anabolic, but it causes blood glucose to go down because stimulates the uptake by muscle and fat. So its impact on plasma glucose isn't the deciding factor. And this is a good point to remember that. Is that good, Morgan? Shall I keep going forward now?
Yeah, sounds great.
Okay. So insulin-like growth factors come from where? They come from the liver under the stimulus of gonadotropin, of growth hormone, not GRH, just GH, which stimulates liver and other tissues. Next question. Quickie, what region of the bone, long bones, are stimulated by growth hormone to make you a pituitary giant if you have excess growth hormone, or a pituitary dwarf if you have too little? And what happens if your excess or deficit comes after puberty instead of before? We don't talk about a deficit after puberty. We usually talk about an excess because usually you have an excess of growth hormone because of a tumor in the pituitary gland that's secreting excess growth hormone, and it's causing broadening of the bones, but not lengthening at the epiphysis. The epiphysis is where the growth plate is, and the growth plate involves adding length to the bone by division of chondrocytes, which are constantly pushing the epiphyses, that's the terminal part of the bone, up to make your bones longer at both ends. So T3 and growth hormone are important for these. T3 and the sex hormones being permissive, and growth hormone being the core stimulator. Okay, final set of questions now has to do with calcium. Calcium. I've got my digital dialogue up. Everybody go to your digital dialogue. Quick, quick, quick. See if you can get in to question number 8. Name 5 important mechanisms that require sufficient extracellular calcium. And here what I'm trying to get you to do is think back on what we've been talking about throughout the course. It's come up several times, but you won't have put it all together till just now. You'll say, oh my goodness, the extracellular calcium level is really important. In fact, you might even remember that I said it's crucial. Homeostatic control is necessary or we die because of one of these mechanisms. The other ones, we don't die, but, well, they could be very problematic. They could cause us to die in some cases. And the second part of the question, what hormone is released from the parathyroid glands when blood calcium falls? And how does it restore blood calcium levels in 3 ways? Taught you 1 in anatomy, those who had anatomy. In physiology, we're going an extra step. We're going to teach you 2 more ways that this hormone increases blood calcium levels. How are we doing? Is everybody in? Is everybody able to do this? I don't know if I can tell or not. Oh yeah, Craig's in, Daniel's in. Raise your hand to Morgan if you can't get into digital dialogue still, so he knows that you're still having trouble. Jacob's in, G3. Between you, you might think of 5 ways. Good job, Joshua. Austin, good job. Oscar, Luke. All right. Let's think about 5 different things that calcium can do. It can be the cement for tight junctions. We haven't talked about that in class. It holds tight junctions together. So that's a new thing, as far as I'm concerned. But important, especially if you're in Dr. Mizrachi's lab. It has a role coming in from outside of the cell in the heart cells, heart muscle, and smooth muscle. It's important for activating exocytosis at the synapse. It binds to negatively charged lipid head groups outside of the cell, repelling the positively charged activation gates of voltage-gated channels, like the voltage-gated sodium channel, the voltage-gated calcium channel. And in doing that, it influences the excitability of neurons. If it's too low, then they are too prone to be in the open state, these voltage-gated channels are. So basically your threshold is reduced and you go into spasm and die. You die for being unable to relax your inhalation. Can't get air out to breathe in new fresh air. Also, remember how it was a cofactor in coagulation cascade? What if it were too low? You would have no cascade, so you could easily bleed to death if you're wounded. So lots of different things that calcium does, and it's got to be maintained at pretty close to 2 millimolar in the extracellular fluid. So what hormone keeps it around 2 millimolar? If it starts to drop, parathyroid hormone kicks in and stimulates the breakdown of bone by activating osteoclasts. Remember osteoclasts from anatomy? It's interesting in today's lecture that they're actually stimulated indirectly. These are the breaking down bone cells, osteoclasts. Clast means to break down. They don't actually have parathyroid hormone receptors on them, but there are nearby cells that are affected by parathyroid hormone that release paracrines that go to the osteoclast and stimulate them. So a little fine point there. And the other fine point that's new here is it's not just the bone breakdown by osteoclast that releases extra calcium into the bloodstream. It's also that the kidneys reabsorb calcium from the nascent urine better, and the intestines absorb calcium from the intestine better when parathyroid hormone is around. It alters calcium transport. Also, parathyroid hormone, it turns out, alters vitamin D synthesis, conversion of D3 into calcitriol, which also influences kidney reabsorption and bone resorption. Next question, 9. 7-dehydrocholesterol, new word, not on the slide, just made it up. No, I just got it from the internet. Undergoes a ring cleavage when it absorbs ultraviolet light. In other words, when you go out in the sunshine. It's in your skin, gets a ring broken, and then with further light, isomerizes, so changes its conformation without its bond configuration. It isomerizes to form vitamin D3. Vitamin D3 is then hydroxylated in the liver and then hydroxylated in the kidney to form 1,25-dihydroxy calcitriol, cholecalciferol, which is also known as calcitriol. What blood hormone stimulates hydroxylation in the liver and kidney of the vitamin D3? And in what 3 ways does this 1,25-dihydroxy cholecalciferol, also known as calcitriol, how are 3 ways that it increases plasma calcium go? Stay with me now because we're almost done and we're getting to the question that Morgan will grade you on. Austin, Alan, Marin, Jade, Oscar, Marin. I'm going to start calling you Marin, even though you're not Hispanic. I just think it's a beautiful Hispanic name, Marin. G3, Luke, Joseph. Marin, do you want to make any announcements? No?
Not sure of anything at the moment.
Good. A lot of I don't knows. Who else is going to chime in? Josh, Jacob, Craig, G3, Charlie. G3 edited his. Well, we're talking now about how calcium makes strong bones. So the answer is, what was the question? Parathyroid hormone is right. That's what stimulates the liver and then the kidney to form calcitriol. This is vitamin D metabolism. Let's think about it for a sec. parathyroid hormone stimulates the kidney to make 1,25-dihydroxycholecalciferol. I guess this slide doesn't show it stimulating the liver to make 25-hydroxycholecalciferol. I thought it did, so I might have jumped the gun on that. I thought I read that on the internet, but at least it stimulates the kidney. So let's leave it at that. The book says it stimulates the kidney to do the second step, adding hydroxy at position 1 on cholecalciferol, which is also known as vitamin D3, to turn it into calcitriol. It was D3 because it was already an all, a single alcohol group, and then had a second one, 25, added at position 25 to make it a diol, and now it's a triol once it gets another one at position 1. So it has hydroxides at positions 125 and whatever the original place was that was there after splitting cholesterol. Position 7, wasn't it? 7-hydroxycholesterol to make vitamin D3. Don't know where the 3 comes from exactly. In what 3 ways does calcitriol increase plasma calcium? It increases it by stimulating bone resorption. I added this a few years ago to this slide. Stimulating calcium reabsorption from the nephron. Stimulating calcium absorption, calcitriol, stimulates calcium absorption from the small intestine. In fact, it's the dominant stimulus of calcium reabsorption from the intestine. So if you want to build strong bones, if you're, for instance, you're a menopausal woman and you're starting to be afraid that your estrogen levels are going to have been dropped, cause osteomalacia, osteoporosis, then you'll probably want to make sure you get plenty of vitamin D, because the vitamin D stimulates calcium uptake into the bloodstream so that you don't depend on your bone reservoir so much. You don't have PTH being released by your parathyroid glands, stimulating calcium release by osteoclasts chewing up your bone. You get enough in your bloodstream from absorption. That's why my wife takes vitamin D every day. I didn't realize that. That's it. And then calcitonin, last question, the one you're going to get graded on, go, 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 comes from where and how does it reduce blood calcium if you get overdosed on blood calcium? How is it the antagonist to parathyroid hormone and calcitriol? And I haven't emphasized at all and won't. Also, prolactin has this place. There's a small role in this. Everybody in? 9:50, we're out of time. You know, Morgan, I just haven't really hit the 9:30 goal at all, have I? Yes, it comes from the thyroid, and it is an antagonist to parathyroid hormone. Namely, where is it? Namely, it builds up bone by stimulating osteoblasts instead of osteoclasts. Plus, item number 2, it inhibits calcium reabsorption from the kidneys by calcium pumps in the cell membranes of the epithelial cells. So calcitonin exemplifies Cannon's postulate of antagonism. The only trouble is it's far more active in lower animals than it is in humans. We really utilize that one type of control much more than the calcitonin control because it's not as effective at building up bone in humans as it is in lower animals. Nevertheless, it's secreted from the thyroid gland, parathyroid hormone from the parathyroid gland, so it's a good counterpoint. That's where we'll leave it today. I hope you all got a chance to answer. By the way, the questions remain open till 9:59, so you could still, in the next 8 minutes, get your answer in. But I will say goodbye and have a good week and be prepared to fast on Friday. Thank you very much.